All right, I am back online. Had a nice little lunch break, had a little bit of a nap, feeling pretty good. Time to get back to doing some questions here. Let me just have a little bit of water right now. So I guess before we begin, I've been trying to do this, just sort of updating people where I'm at. I know obviously if you just jump in at some random point live, it's going to be unlikely that I'm going to be explaining what I'm doing, but these videos will be around later. And I'm imagining that if somebody perchance is watching this video, maybe months or years later, maybe they will want to know where I'm at right now. So we finished all the lectures. I've watched all 24 of the lectures now. Now I'm working on problem sets. Again, I had done 4.5 of the problem sets. I was finishing up problem set 5. And let me just switch this over to this one here. This is problem set 5, right? And I had not finished problem set 5. Part of that was because it was involving some stuff with the simple harmonic oscillator. I didn't feel super comfortable with some of those results. So I even went back, did some kind of Feynman technique-ish things with those lecture materials, textbook, spent about a day doing that. And then instead of going back into 5 immediately, I decided to push forward and try to finish all the lectures. I did want to see the whole class. This has been something I've been talking about kind of from the beginning, that I like to see everything before I decide where to invest my time and what to focus on. The disadvantage of that, obviously, is for a cumulative subject, of which this is, you can get into trouble if you race ahead, you didn't understand the starting concepts, and then you're having more issues. So it's a balancing point. I've chosen to do this in kind of the 2 chunks, first 10 lectures, first 5 problem sets, and then do these. But I mean, that is a sort of arbitrary decision. I could have decided to do it exactly as you do in the class, where you do the problem sets exactly in sync with the lecture pace. That would have also worked. Or I could have done it where I did it like the MIT challenge, where I just do all the lectures all at once and then go into problem sets. Thinking back, knowing what I know now, but having gone through the material and the difficulty of the problem sets, I might have split it up even more, just because I know how difficult they are. Generally, I find if the class is a little bit on the easier end and you are squeezing in time for class where you're not necessarily drilling down every single concept, you're drilling down a few weak ones and you get quite a few other ones, then the full coverage, full problem set method works better. If it's going to be a real struggle of a class, then doing the step-by-step approach is probably better. So I would say that midpoint also depends on difficulty. So for me right now, this 2 split is probably a little bit, I maybe would have done it in 3 groups. I don't know. It's hard to say. It's hard to say, really. You just don't know when you actually start working what it's exactly going to be like. And one of the things that I can say that it has been like that is not, wasn't obvious to me when I started, is that this is a hard class. Now, I know obviously quantum mechanics is hard. It's a hard class, obviously. But I think there's a couple factors that are making it extra hard for me. So one of them, as I mentioned, is I didn't do 803. I thought that it wouldn't be too important for 804, and in some senses it's not. In some senses, a lot of the stuff we're doing, I think, is unique to 804, operator notation, a lot of this kind of thing. So I don't think it would have been necessarily worthwhile to have done all of 803 first, if it was like, trying to efficiently learn this material. But in the same sense, it does add an extra difficulty level. The other thing that I'm realizing or recognizing right now as well is that the physics and calculus-based classes were always more challenging for me in the MIT challenge. That could be just because they're intrinsic difficulty. It could just be because I just had a kind of intuitive grasp for doing the kind of discrete problems that came up in computer science a little better than the kind of continuous sort of integrals, differential calculus stuff that was coming up in the physics-based classes. And so this class right now is fully in the physics stream. So whereas when I was doing 801 and 802, they were challenging, but those are general requirements for all MIT students. So in some senses, they might also be a little bit easier because you're having all types of students take those classes. not necessarily ones that are going to specialize in physics. Now we're in 804, only physics students remain pretty much. I mean, there might be the math student or engineering student or something like that, but basically it's it's just physics students. And so that's also, that filtering effect is making it a bit more challenging for me as well. You've probably experienced this as you've gone further into some fields. You might find that the classes become harder, and some of that's because the difficulty is getting harder, but some of that is just because if you're in a difficult field, as people fall off the difficulty rungs, as you get further and further, you're in a more rarefied group of people, so all the people are pretty smart, pretty practiced, and so the expectations just get higher. I remember talking to someone who was doing a PhD in physics, I believe, and he was just sort of commenting on how difficult he found all of it. And my explanation was, I think that's the reason. It's just because very few people get to a PhD level of physics, and the people that do were really good at physics, like almost guaranteed you were good in your physics undergrad if you're doing a PhD, as well as you were probably smart and this kind of thing. And so it's just not possible of all those people for everyone to be above average. This isn't like Wobegon. So that can create some difficulties. And I might be feeling a little bit of that right now, just because the expectations for mathematics, the expectations for solving problems are just a lot higher. So how am I dealing with it? Well, I'm going to work harder, right? I'm not going to give up. I'm going to try to keep practicing. So what I'm going to try to do now is just continue working on the problems. We're still finishing off 5. I'm going to get to the end of the day, and then near the end of the day, around 5 p.m., I'm going to make maybe a decision of what I want to do next week, how I want to approach it, because I'm a little bit worried that I won't reach my kind of set goal of passing this final exam, or like definitely passing the final exam. I wouldn't want it to be just, well, I just happened to get the right questions and I got lucky, so therefore I passed it. I would like it to be a strong pass if I'm going to attempt it, because I only have the one shot. And so given that, I've been sort of thinking in my head of whether I want to, really push it and go more time into this project. A lot of it was sort of working around different constraints, and so I have to keep in mind that I have to work and I have to do other things on top of this. Not a ton of work. I'm not saying that I'm working full-time in addition to doing this, but there's definitely some factor there of work that I have to do. So I might do a little bit of work over the weekend. And so I'm kind of thinking in my head right now, do I want to do something closer to the MIT challenge schedule where I'm working all day instead of just in these 2 chunks? And so I have to think about that a little bit, because in one sense, I definitely want this project to be successful. I want to succeed at it. If I'm going to fail, I'd rather fail because there was no way I could have done more, rather than fail because I decided not to work as hard as I could. But at the same sense, I'm also thinking that I'd like to I'd like in these projects to kind of talk about efficiency and not just talk about, well, the way to succeed at this is just to study nonstop. So for me, I prioritize succeeding at this project than trying to control the number of hours for, some sort of arbitrary reason. But I have also tried to do that in some projects of being more explicit about how many hours I'm putting in, because obviously if you put in, 16 hours a day, it just becomes less approachable as a model for other people to use. So we'll see. I'm going to make that decision at the end of the day, but I'm just letting you know that it's in my head right now. So I've been wasting enough time chatting about this. Let's get back into problem sets. So part C is to find the expectation value of this momentum operator for the for this particular state of the where it's 1 over root 2 psi naught, meaning the first energy eigenstate, plus I times the psi 1. So this one here, I'm gonna just do it. I'm gonna do it the old-fashioned method, because that seemed to be I was getting a bit stuck with it on the position one, but I was getting the right approach. I think it was just some of the math of using the Gaussians and stuff that I wasn't sure exactly how they were getting it. So there's probably some there's probably some things that I'm working here. So we can I do the Fourier transform of these so that I don't have to do this IH bar stuff? So there's kind of two routes I could do this. I could take, so I could do it like this, where I do it in the position domain, and I do basically psi complex conjugate, p hat of psi. I could do it this way, or I could try to do it with, what is it, 1 over root 2 pi, and then do dk, and then we do psi tilde this. And would it be the momentum? I think would it be? It wouldn't be the momentum operator here now. All right, I think I'm going to not do that. I don't remember learning that, and I might be making a mistake in assuming that I can do it in momentum space. So is there any way I can simplify this? Because I do feel like this is often an issue that I have, where I get into these big complex integrals and then I screw it up because I don't recognize something about the problem that makes it easier to calculate. So let's just look at it for a second. I don't see anything obvious here. All right. So I'm just going to pull the 1 over root 2 here, and then we're going to have phi 0 plus I phi 1. And then this is momentum operator I h bar, I over h bar. I always screw that up. Let me just check the momentum operator. Yeah, h bar over I, so minus I h bar. Maybe I'll just do h bar over I. Just got to keep in mind that these are multiplying against each other. I'm worried if I have the minus sign, I'm going to copy down. Ooh. Get the right order here. H bar over I. Derivative with respect to time of, this is conjugate. So it's going to be, we can just do minus sign. So this explanation here is that we are able to treat these as real. So psi equals psi naught for that, and then we just add this minus sign times dt So this is probably easier than I'm thinking because we only have a phase there, right? So let's pull out the h bar over I. And then we have time derivative of this. Well, another way of saying that is going to be that we have ddt of, and then we've got psi 0x e to the, what is it, minus I omega naught t divided by 2. and plus I psi 1 x I omega naught t. So this is 3/2. Oh, E. Oops. So let's take the derivative now. Oh, I should put dx here. Dx, dx, dx. Okay. Let's make this right. And then, well, we're going to have two parts for each of these here. There's no time derivative. This is just a constant. So we can basically just differentiate this one because the other one's going to have no x dependence. And when we subtract off, take the complete integral, it's going to get eliminated. So we can do I minus I. And then this is going to be plus, because we got two i's, and that cancels. 3 has omega naught t. All right. Let's get this guy over here. Okay, what do we have here? This is psi times psi naught. So this is going to be the norm squared. Oh, hold on 1 second. Hello? Oh, downsides of expecting a call is that sometimes you get spam calls. All right, let's go back to it. So this psi is going to be psi norm squared. So it's just going to be 1, but I'll leave it there just for right now. And then we're going to have I over 2 e to the minus I omega naught t over 2. All right. And then we have this times this. So we're going to have plus, I'm going to put ding 1. And we're going to have 3 omega naught t over 2 e to the negative 3/2 I t. Should probably pull the I out. All right. Those are our two terms here. And then we're going to have a minus. So minus and minus, but then the i's cancel. So we're going to have minus omega naught over 2. 1, 0. E to the negative I omega naught t I by 2. And then we're going to have these ones. And then it's going to be minus I minus I 3 omega naught t over 2 norm squared 1 sine 1. And then this e to the 3/2 I omega naught t. All right. So we have 4 terms here. What's going to happen? Well, we know that this is going to become 1 in the integral. We can use, because these are all linear, we can just separate them. So this is going to become 1, and this is going to become 1. So we're going to have h bar I over 2, and then it's going to be 4 terms, and those terms are going to be I w naught 2 plus, and then let's get this guy over here, same deal. This is a pure phase, that's going to integrate to 1. This is going to integrate to 1. So we're going to get minus 3/2. So this is, I'm going to put I 3/2 w naught. All right. Oh, no, sorry, not supposed to be a t here. I'm bringing it down inappropriately. Nope. This is not supposed to have a t either. And so these are our 2 kind of plain terms, and then we're going to have 2 remaining integrals here. Dx, and then one of these is going to be sine on sine 1 times this big mess of stuff. So again, we can also ignore these things because they're also going to just integrate to 1, I think. Is that going to be the case? No, I think I should leave them in. I don't know that I can remove them like that. They are pure phase, but they're multiplying these things, so I can't just remove them for linearity. So let me just put it like this. We've got 0, 1, e to the minus I, and then we're going to have 1/2 plus 3/2. Well, that's just going to be 2. So we can just 2 WOT like this. And then this minus no, that'll be multiplying. I'm not sure I can do this. What am I doing right now? No. And then I have so 3/2. So we're going to have all right, now I think we have to know the form of these equations to be able to get it right. So I'm just again going to put h bar I. So let's just get rid of these minus I on top. Just multiply everything by I. And it's going to be I negative I times this by, we're going to get negatives, positives. So I think we can just get rid of the I. So we're just going to have 2. And then this minus this is just going to be minus 1/2. These are plus, actually. So this is just 2. So 2 root 2. So we can just have negative naught. All right, let me just walk through what I'm doing here so I make sure I don't make any mistakes. This is going to be 2 root 2 plus 3/2. This is root 2. This is going to be 2 over root 2. So I can just put root 2. W naught H bar. I believe that's right. Should be. This just becomes minus 4. Factor of the minus I divided by I. We just multiply by this minus 1. Did I lose a minus sign? Yeah, I lost a minus sign here. Okay, and then this is just plus this whole mess. Now, yikes, okay. So this was, let's just double check the form of that. That was M. All right, this is 1/4. X root 2 over A x squared minus 2A squared. So this is this, this is this, and then we have our 3/2 not. Oh boy, all right, let's try this. Minus root 2 H bar. Well, I think we can pull out this factor, which is going to be times square root of M W naught pi. And then we are, so we can pull out this factor. And this is just 2 times this. So we can just get rid of the A. So we have dx. We have x root 2 over A e to the minus x squared over A squared times 3/2 omega naught e to the minus 3 omega naught t over 2 omega naught. Just put 1/2 halves. That makes it a little bit clearer. Minus 1/2 omega naught t to the minus I omega naught t by 2. All right. These have no x dependence. Is that gonna, the fact that those have no x dependence, is that gonna cause any issues? I think because these have no x dependence, this stuff and this stuff is going to become 1 in the integral. No, it's not going to become 1 in the integral. It's going to stay this here. But we can pull it out because it's not a factor of x. So let me so let's try that. Can everyone see? Is this, do I have my camera? I think it's a little dark in here. I've been finding it kind of tricky to control the lighting because it's always changing and I don't recognize when it's getting too dark, too bright. It's a little better. Okay. All right. So we've got or not h bar, pi. Oops. Pi h bar. And then this is plus, well, this, can we express this as sines and cosines? Is there an easy way to do that? This is minus, oh, no. We've forgotten the I. Why do I have the I still? I forgot to take it down somewhere, I think. Where did I do the derivative? No. I think maybe I maybe just got rid of it by accident over here. So it should be e to the minus I. Okay. Oh. All right, I gotta be careful where I'm putting things. Minus I. This is minus I. Omega naught over 2. And then we've got and this is the same psi 0, psi 1 term. Now we did this one last time. So this is how they did it, and I'm just going to expand it here rather than rewrite everything. They went, this is equal to from positive infinity, negative infinity, dx of x squared. Hold on a sec. I shouldn't be doing this because we've already flipped it over. What do I have here? We have x over a root 2 e to the negative x squared over a. Why do I not have it in the same form they did? Oh, okay. So hold on a sec. They did it in 3 steps. We have x root 2 over a e to the negative x squared over a squared squared. And then they did this. Is it just a or a squared? Yeah. How did we get ax over a squared? Oh, shoot. How did this go? So they keep it like this. And how are they? So we have an a underneath, and we want 2 a's underneath, so we have to pull an a up top. So I think they do this. Yeah, that makes sense. And then they do a substitution of variables. So they say let u equal x over a, and then we have du of u squared e to the minus u squared. And then I guess this is a known this is a known integral, which I don't know what the form is, but what was the answer they got? Does this just integrate? What does this integrate to? It's like root pi over a or something? Root a over pi? Let's see if I can, I'm gonna just throw out Mathematica to see if I can I don't know whether can I do, I don't know how to type it in here. Integrals, integrate. Okay, let's do it like this. So we want to integrate x squared e to the power what is the ex squared 2 minus 1 to the 4th root pi. I'm just going to look. Oh, what is this? Imaginary error function. This is what, integral does not converge. Oh, that's really. Oh. All right, let's just do this. Yeah, root pi divided by 2. So this becomes a times root pi divided by 2. Let's go back to our problem sets. Okay, let's see if we can solve this now. Is equal to minus 2m omega naught cubed for pi. And then we've got a root pi over 2, so that's going to cancel with this. And then we have an a. And this is also multiplied by 3/2 omega naught e to the I3 omega naught t divided by 2 minus 1/2 omega naught e to the minus I omega naught t divided by 2. Yeesh. All right, so we have this is where I lost an h bar. So this is a h bar. We can square this, so this is omega naught to the 5/2. Yikes. I. Somehow I keep dropping my I there. EI omega naught. I2. Well, this is some sines and cosines. There's nothing obvious that's coming out to me of what those are in terms of sines and cosines. What was our definition of A again? A was this. So let me just replace it with the closed form. So A is root h over m omega naught. Did I lose an m too? I also lost an m. Oh god, I gotta be careful. All right. You know what? I'm just gonna put this all in a h bar m. Yeah. Okay. So we're gonna do this times fifth. So we can just cancel here, and this will become fourth. Cancel here entirely. And we have this whole thing becomes h bar 3/2 omega naught fourth does this make sense in terms of units? What is the units of omega bar? Well, it's angular frequency. So this is what this is. If we do dimensional analysis, Thanks. All right, we have kilograms. I think this is definitely shouldn't be 3 to the half, 3 halves. So I've definitely got some units wrong here. I mean, maybe this was supposed to be squared. Because there's no way this is going to work out, is it? So we want a momentum. Momentum is mass. So I'll just put mass, kilograms. We want this. And what do we have? We have this is joules. Joules seconds. So that's joules. Meters squared, seconds squared, seconds. So we cancel one here. We get to the second. 3 halves. How are we going to get that's not right? So we're definitely wrong on the dimensions. And then we got the square root of 4. So this is just squared. That doesn't look too bad. Still looks wrong, but and what's the form of these here? These should just be dimensionless, right? Because we get time 1 over time. So where did I drop? Let's just walk through my calculation and see where I made my mistake. H bar over I ddt s. We move the H bar over I here, so you still got H bar. We pulled out an A here. Did we pull out an A anywhere else? Like, is this supposed to be A squared somehow? So we're dividing out by another A. Oh, wait. This is 1 over A, right? Did I pull out a 1 over A in this one? Yeah, 1 over A. 1 over A. Right? Because we get... And that doesn't make sense. Why is it 1 over A? Okay, let's think through it. We want this to be in this form. We move the root 2 out. Did I move the root 2 out? I don't think I did. So for this to be squared, so we divide everything by A. Multiply this by A, divide this by A. That should cancel, right? Okay. We forgot the root 2 somewhere here. What was A again? A was square root of h bar m over omega naught. What should it be? Just dimensional analysis wise, what should it be? To get a kilogram meter square, we should be able to have this should be kilogram meters per second. And we have these two. Do we have any other constants? I think it's just these two, right? So we have kilograms, meters squared, second minus 1. Do we have any other units in this problem? There's, yeah, h bar, omega naught. We need to remove a characteristic length scale, right? So we need it to be this. Kilogram meters per second, and we have kilogram meters per second. Yeah, let's just use dimensional analysis to try to look at this. So we've got also, I guess we get kilograms. So if we were to get a kilogram mass second, what would we want? We would want maybe root. Is there any other constants? What we would want, we need, for kilograms, we need 1. For meters, we need 1. And for seconds, we need -1. And then we have alpha plus this. And we have 2 alpha. This one we have minus alpha minus beta. So alpha is equal to 1/2. Mass is equal to 1/2. We have 1/2. It's also this. So they should all be 1/2. Does that give me the right amount? Let's just see. If we have square root of all this, we're going to have kilograms. We're going to have meters. We're going to have seconds. So what we need to have is square root of h bar m omega naught. This is what our dim analysis should give us, and we're getting this 3/2 garbage. Where are these constants coming down that I'm doing this? this here. So 1/2 h bar over I. We pull the h bar out. H bar over ti over root 2. Where'd the root 2 come from? Oh, over here. Okay. All right, and then we take the time derivative of this. It's going to give us this. That's going to give us this. This is no dependence on time, so it'll be fine. This. Still only got omega naughts here. Omega naught 1 to the 4th, 1 to the 4th. So these multiplied, you get square root. Where did we pull out this omega naught? I think I've doubled the omega naughts because these are plus. Yeah, this was plus here, and I multiplied it. So this was plus, and then let's just pick up over here. I'm just going to rewrite it so that I don't make this mistake again. Over pi, omega naught cubed. The hell is that coming from? That's not coming from anywhere. Oh yeah, it's 3/2. No. So this is, I made a mistake earlier than this. Let's just change it in the formula here, because sloppy arithmetic, guys, got to be careful. All right, so we got this. It was multiplied by a bunch of this stuff. We had this factor. This factor, we got this. So one of our terms here is going to be, I'm just gonna put it here. So we have minus root 2 bar omega This looks like the wrong units as well, does it not? Shouldn't it be a root of all this? All right, and then we've got these things plus. So we're going to have plus omega naught pi times this whole jazz. And then that's going to be 3/2 omega naught e negative I d over 2 minus 1/2 naught. 2. And then here we have this a by pi by 2, but a we already know is root of h bar multiplied by h bar m omega naught. And I think because we have that root 2, I think the root 2 is just going to come down here. So we can just go pi root 2. All right. So does that get us closer in dimensional analysis? Well, we lose this, which I guess is good. This one's a root. This one's not. Oh boy. And we're going to lose these pi's here. So this simplifies to I just flip back and forth. Simplifies to root 2 omega naught h bar plus this is disconcerting because this is not giving me what I was going to expect. You don't even have the right dimensions here. This is our answer, but this cannot be right. For one, we've got this is in units of kilograms meters squared. This is in units of energy, and this is in units of, well, who knows what. So there's no way that this is our answer. Let me look through it again. I'm going to look through it again and see if I made any mistakes, and then I'm going to go to the answer. All right. Let's walk through the calculation one more time. So we take the time derivative of this. So it's h bar over I ddt this, which is the same as moving the h bar and I here, taking these time derivative of these. When we take the time derivative of those, though, we drop down I h bar over I omega naught 2, 3 omega naught over 2, psi x this. Okay. And this is going to be h bar I over 2. Well, we multiplied it out, so we went these guys. So it was norm squared of this times this. Now I deleted this, but that was not right. Because this is a time dependence. Ah, there's my mistake. Okay, so let me back it up and start from there again. So let's say, okay, let's start with a new thing. So we have h bar over I root 2. And we have e to the I minus I. E to the minus I 3 halves omega naught t. Then we had plus, that was minus actually. Minus I 3 halves t. Oh, let's not do it like that. Let's put all our size first. So this is norm squared side 1 minus I 3 halves omega naught e to the minus I 3 t. This should be our integral. So we have 4 terms here. And these are going to be 1, but they're going to maintain this time dependence. So I'm not going to be able to add them. And that was my mistake. So h bar I root 2 over I root 2 is equal to, well, we're going to take the integral of this, and it's just going to be this. So we're going to get minus I omega naught 2 e to the minus I t over 2. And then we're going to get this one here is going to be also 1. So we're going to get minus, which is plus I plus I 3 omega naught over 2 e to the minus I 3 omega naught t. All right, so we've got these terms. So we can cancel this, but we can't cancel that, which I was trying to do foolishly. And then we're going to get the plus of these 2 factors combined. So we had what? So we had well, we're going to have phi 0, phi 1, and we're going to have this minus this, which is a plus. So we're going to have 3 omega naught 2 8 I 3 plus minus I omega naught t over 2. Right? Do we have correct units now? If you know how regards we integrate this thing, we have h bar omega naught. It's no mass. This does not look like the right units. I guess this is still imaginary. So I can influence things. Oh. I think it's time to look into the solution. I really thought I could get that one. All right. So where are we here? All right. So obviously, so we got this part right. All right, and then this is going to be h bar over 2i. Oh. Yeah, that's bad of me. Forgot I was multiplying it twice. All right, already some mistakes. And we're going to have e to the I omega naught t 2 star 0 minus I e I 3 omega naught t over 2 1 e minus I omega naught 2 dx. Oh my God. Oh. Wow. Wow. All right, that's why we're getting it wrong. I'm forgetting, I've miscopied the appropriate formula for the momentum operator. Terrible. Wow. Okay. Plus I e to the negative I3 omega naught t divided by 2 times 1 prime of x dx. Okay, so now this is now a completely different problem. I'm trying to integrate these phases. Oh, I got it mixed up with the energy operator. It's t. It's the derivative in x. I think it's just because momentum, I'm used to it being something that changes in time. And I forgot that for quantum mechanics, dx. Which I mean makes sense, because otherwise it wouldn't give anything for these. The momentum operator wouldn't be right at all. All right, so where we once again use the fact that energy eigenfunction be taken to be real. Let's examine this term by term. Since the derivative of an even function is odd and vice versa, terms like phi n prime must be odd overall. We thus have, I'll just put f. F odd prime is equal to even function, and f even prime is equal to an odd function. So we're using symmetry. We get equal to h bar over 2I. So that means, oh, I should have put that up here. H bar 2I of psi 0 prime plus psi 1 prime minus I e to the I omega t psi 1 psi 0 prime plus I e to the I omega not t. Why is that not 3/2? I guess the idea is this minus this is going to be e to the I3 omega naught t divided by 2 times e to the minus I omega. Oh, I'm writing on the next page. Oops. I to the omega naught t divided by 2. So these just add, and then this one is going to be the opposite, which is going to be I omega naught t 2 minus omega naught t over 2. Okay. Psi 0 psi 1 prime dx, and using symmetry, so since these are all odd functions, they should all be 1. Is that right? Is that the idea here? No. Oh, that's just for these ones, or just for these ones here. So h bar over 2I. T psi 1 psi 0 naught plus I psi 0 psi 1 x. And then this is going to be equal to 1/2 root m h bar omega naught pi. Where did we get that from? How do we go from 32A to B? How do we get I'm going to work this out with pencil because I don't entirely understand the math here. So let me just put this out here right now. So we have these two guys, and that's going to be minus I e to the I omega naught t. And then this phi 1 is equal to our what's our value there? M omega naught pi fourth x root 2 over a e to the x squared over 2a squared. And then this prime is going to be the first derivative of, so let me just write those out. Arrow naught prime is going to be, what is that? That's m omega naught pi to the 1/4. Should probably, yeah, I'll just leave as GDX. All right. Where are we? E to the minus x squared, a squared. What is this? I've got to learn these. Okay, so no, you know what I'm going to just do? is equal to -2. Oh, actually, what is chain rule? I think I should know this. Just remind myself. F prime GG prime. So it should be just x over a squared. No, a squared. Because we've got should be x over a squared times e to the do we lose the so we get the 2 and we lose it, and then we'd have the minus a, and then it would be minus sign, I believe. No? Does this make sense? Let's just gonna check with Wolfram also, just to make sure I'm not making. Yeah, that should be right. Okay. All right. So we've got this, and then let's go 1 prime. It's going to be this and omega naught pi 1/4 plus. And then we have x 2 over a e to the minus x squared over 2a squared. So we're going to have this here. So chain rule is going to be x squared minus x squared root 2 over a squared. So we'll take the derivative of this guy and that alone, e to the negative squared over 2a squared. And then we're going to add derivative of this, which is just going to be minus 1 over a squared e to the negative squared over 2a squared. Right? No. I don't know if it's going to be derivative of this. It's just going to be plus root 2 over a. So given this, what do we have here? Well, we have h bar over 2I. And then let's consider each parts. We have minus I e to the I w naught t, and then we're going to have this awful mess, which is going to be psi 1 This is 2 here. Oops. Should have 2 down here. And this should be 2, so this should also be root 2. Oh. Two over A. Two A squared. This is our psi 1. And this is going to be times psi 0 prime, which is going to be m omega naught pi, the 1/4. And then it's going to be x over minus 2a squared e to the minus x squared over 2a squared. And then this one is going to be what? This one is going to be dx. I e negative I t, and then we've got this 0, which is going to be this squared, and then that's times this, which is going to be minus x squared over root 2 a squared e to the minus x squared over 2a squared. And so we can right away go pull these out. So we go bam, 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 and we have equals h bar square root m omega over pi. And then these two things here, what's that going to give us? Well, we're going to have, you know, I'm going to just, I'm going to redraw on the next page. All right. So I still don't know how we're going to get this, because we should have a, what is it? The units should be root h bar. So I don't know where we're going to get that root from. Oh, there's an A term. Okay. So it'll be fine. All right. I'm just going to rewrite a lot of stuff on this equation. Jeez. All right. That's root 2 over A. And this, I'm going to put this next. X over root 2 A squared. All right. And then it's going to be e to the negative x squared over a squared plus, I'm just going to put this here, I'll put dx minus infinity I e to the negative I w naught t. Now what do we have here? We have two terms. We can factor out those, so we can just go minus x squared a squared plus root 2 over a. So I've got these two expressions now. So the fact that this has a cubed here and this has an a squared and a is very worrisome because we're not going to end up with the same units. Let's look at the solution for right now just to see what I'm missing. All right. They have three terms here. So what are their terms? Let me write those down. So they have, let's put a bracket on here. They have is equal to well, they've got the 1/2 h bar over m0. Crap, how did we get the h bar into the square root? See, I don't understand how the h bar got into the square root here. Because it was strictly outside of the integral. So they factored out the I here. Is divided by I. So this can just be 1/2. So that makes sense. All right, so we got 1/2. But how do we get a square root? We must have divided by an h bar somewhere. That means an h bar must have come out of this. Do we have the close? Where's the close form to these guys? And we don't have an h bar here. I mean, there is an a. But we're carrying those. So I'm going to write this down, but I don't think I've convinced myself I know why it works this way. H bar omega naught pi. How did we get? It wasn't up here. So it has to have happened between these two steps that we got the h and to get the right units. What is the h bar unit again? This a was equal to what? Omega naught over h bar. Where did I write down what a is? So how would we get the h bar? Yeah, I don't see it. Oh, all right. Let's just write it out. G, G. And then they just did substitution of variables here. Should be a minus, yeah. I sine t 2 pi plus cosine t minus I sine t 2 . Well, I mean, when we think about it, this makes sense. I'm not clear on all the steps of this calculation of how we perform this. I mean, it's just integration, but I think I'm missing something. I'm making some kind of mistake, and that's why I'm screwing it up. But this does make sense because cosine's derivative of sine, it would make sense that the positional derivative of the expected position is the expected momentum. I mean, with the appropriate units and everything. So, I mean, this isn't terribly surprising, but how we derived it was challenging. Definitely going to have to come back to that at some point. All right, let's start a new question. D. Show that the probability distribution of a particle in a harmonic oscillator potential returns to its original shape after classical period t equals 2 pi. Well, this is a kind of visually what we should expect is that sort of the classical case of this is that you have kind of this and then this and then this. So it kind of just goes back and forth. So this would be the This would be the wave function quantum mechanical version of this problem. So this, I don't know how to draw that, but if we had like a slosh and then it would go slosh over here and then it would go back and forth. That's basically what we want. So any harmonic oscillator state, including non-stationary states, what feature of the harmonic oscillator makes this true? So we've done this with a particular state, but we need to show this for any state. So we need to show, how would we go about proving this? So essentially we need to show that psi x of t is equal to psi x of t plus 2 pi for all psi. So I think a good way to start would be to look at the Schroding revolution again for this system. So for that, we're going to have what? We're going to have let me get my thing back over here. Do I want to write it like this? Sure. Does that give us any help with periodicity and time? Well, what's going to happen if we set this up in any state? It's got to evolve according to this. How do we show that it's going to go back? I think basically we have to show that at 2 pi, all the phase terms are going to cancel out. So the eigen states of energy return in 2 pi. Is that true? Well, if we look at the eigenenergy states for this system, what are they decided by? So five n is what? It's 2n plus 1 over 2 . not this. This is En. En. So each of the eigenstates rotates with the phase. Phase is always different, but what happens at time 2 pi equals? So let's say we have phase 1, which is going to be e to the negative I t negative I. Three halves. So we can just say generally the phase is going to be e to the I 2n plus 1 over 2 omega naught. Omega naught t. And if we set so we want to say e to the negative I 2n plus 1 over 2 omega naught t is equal to e to the I n plus 1 over 2 negative naught t plus 2 pi over omega naught is equal to e to the negative I 1 over 2 omega naught t about 2 pi should maybe do it like this. Plus 2 pi. So how do we get rid of this? 2n 1 over 2 e to the I plus 1 over 2 pi these are going to cancel, and then this is going to be e to the negative I 2n plus 1 pi. So this is always for all n is equal to 1 because we're always rotating. So since this is the only, so I'm going to say because all eigen energy, so this would be my reason why. All right, let's see what this is for D. This is the operator method. I'll try to look at it again for that as well. D, any wave function can be expanded in terms of the energy eigenstates of the system, okay? Where E and N is the energy of the nth excited state. With the harmonic oscillator, we have E to the N is equal to this jazz. So the wave function takes the form blah, blah, blah. Each term in the sum oscillates with a period 2 pi over n, make it not for some integer fraction. For example, thus after time t, all the phases will be aligned once again, except for the phase in the prefactor, so that psi x of t plus t is equal to the prefactor. I guess just because we can take a phase here. Periodic because the difference between angular frequencies are rational multiples of a common value. The harmonic oscillator in particular, this arises because the energy levels are equally spaced apart. Okay. All right. Okay, let's go on to question 4. All right, let's this be the normalized ground state of the harmonic oscillator. Whereas the lowering operator is the raising operator. Recall the commutator, equals 1. Show that the norm of the unnormalized Okay, so we have to show that this oh boy. All right, so what is our definition of this? Is equal to x bar of 0 minus I p hat over p0. Am I forgetting an h bar? I don't think so. I think that's right. Yeah. Oh, yeah. I wrote it down here. Okay. All right. So when we take how do we get this factor of n? And this is let's just work on this case. Maybe just do. So let's try it. Let's just try it with the square first. And then we've got minus I x p hat 0 p0 minus I x hat p0 x0. Then this is minus so this is going to be equal to x bar. Can I make this into a commutation relation? These are both minus, right? So I can't make that into a commutation relation. Essentially, what we're saying is that A is a unitary. How do we show that the operator is unitary? I'm not sure. Let's just try applying this to minus h bar over I. Do that twice, it should be h bar squared. Then we have x non-zero. That's right, I think. Because we have the chain rule of x not 0, and that gives us derivative of x, we get this. Taking derivative of the other one, leaving x, we get that. This isn't illuminating for how we're getting the norm. What would be another way of getting the norm? Recall the commutator v is equal to 1. Factorial. I guess because we're summing states. That's what I'm thinking here. Do I want to express this? I don't want to expand this. Is there a way I can do this without expanding it? How else could I show this operator scaling it by that factor? Well, this is challenging. I don't really want to expand this out. I think that's going to be super messy and not helpful. What other options do we have? Especially because we're trying to do it for n. You know, like n doesn't seem to be. I think like there's got to be something with the operator to do this, right? Like the operator, this operator A adjoint. Every time you do it, we're increasing the number of states. Is there some way I can see that here? No, I'm going to look it up. I'm stuck. All right. First, remember what it means when we take the Hermitian conjugate of an operator. Okay. Let me write this down. Nope. Norm squared bar state is given by the x So let me write down exactly what's happening here. We start with the definition of the norm. So, okay. The x. So we have so why did they do this? Well, so if we look here, expanded this out into iterated series of raising operators applied to the ground state complex conjugate times the regular version. And then they subtracted one off. I don't understand this intersperse thing. How are you allowed to do that? This I understand. How do you do this? Because this should just be 1. Right? You lower something and then raise it, should give you the same thing. So how do we lose an n minus 1 here? If we can factor out this one. I don't understand how we factor out the adjoint. This must be something defined by the adjoint. Let me look at the problem set again. Is there a definition of the adjoint operator? Where did I write that down? Go to math aside. Where was that? Operators. I wrote it in here somewhere. I'll just put it up here so you guys can see what I'm doing. All right, this was the operator method. Okay, where was the math aside? So this is just the definition. Okay. This is why. All right. That's how they're doing this. Okay. Remember. So we do adjoint, adjoint, and pull this thing out. Okay, that makes sense. Now this can be rewritten in the following way. So now we have A hat, dagger. All right, let's put these hats on these guys. All right, so this is just add 0. Nothing crazy there. Equal to the commutation relation of this plus A dagger A is just equal to 1 plus. Okay. Yeah, because this is just the commutator. So we are commuting through right here. Commute. So now we have a plus. So we have this norm squared. So this is just equal to this plus oh. Plus 1/2. But the expectation value of the energy is constant. Which will just give us E n minus 1. We should have had an H here. Yeah, it's just not showing up. So that should cancel. And we should get I gotta see the latex. I'm pretty confident this is this. Not this inner product, but it's not being rendered properly. And we have what? -1/2. How are we getting this -1/2? Okay, because we're subtracting. Okay, yeah. All right. So we can just nuke that, right? So we have one. So en -1 times 1 dx. Oh, that should not be en. Let me change this to n. N -1/2. This is just going to be n -1/2. Well, minus this off, and it's just going to be equal to n. And then if we go all the way down to 0, each factor is going to be equal to n times n. So 1 n -2 dot dot dot. Oh, dot dot dot. Just going to be 1. So we're going to have n factorial, which means normalization. Oh, this is too low. Normalization is n factorial. Wow. Oh. All right, boy. Okay. I'm gonna go for another Yeah, I'll go for another 20 minutes. C. Show, oh, this is not C, this is B. B, as a consequence, the normalized energy eigenstates take the form. Verify these eigenstates are orthonormal. Show that let's go back to our definition of that inner product. I know it was around here. Bum, bum, bum. So we need to show this. Okay. How do we show that? Oh, sorry, not 0. Yeah, no. Yeah, I didn't understand this little D notation here when we were doing that previously. It's not 0, it's this thing. Do I want to take the actual states? I don't think so, because we have to do it for arbitrary ones. Well, we do have the kind of closed form with the Hermitian, so it would be something like HM X. This is the Hermitian polynomials. E to the negative squared over 2a squared. Complex conjugation. HN. We should be able to just reorder terms here. So I think these two should just be equal to 1, right? So I think we can just cancel them because magnitude of the Gaussian. I mean, this is going to have some normalization constant here too. So I think that's just going to be equal to 1. It would stand to reason. I mean, well, this is purely real. I don't think, yeah, so it's just 1. And we take it all over x, no? I'm going to drop the 2. We're just going to get this 1 over half a squared business. But I feel like that would have been in the normalization constant. Because we're assuming these have some normalization factor. So can I do this? Is this? Can I do something like I think this D and M is 1 if n equals m, 0 otherwise. I think that's what that means. What do we know about the Hermitian polynomials? They were related by that form. What was it? AJ plus 2 is equal to what? Where do I have this HM? Where do I have the expression for those? I feel like I need to know something about the Hermitian polynomials to say this definitively. I'm not sure that they're orthonormal. Maybe I can just do a non-mathematical argument. I can just say if they weren't orthonormal, so if I said something like, if they weren't orthogonal, could construct state we can construct a state phi m equals phi, let's call it phi a plus phi b. And if we could do that, I'll just do a phi b. If we could do that, this would lead to a contradiction. How would I show that? Well, if we took the annihilation operator, how do I show this? What was that energy operator I wrote down? You see, these would also be eigenstates. So if we took the energy operator on each of them, we should be able to do So how do we show we can't do that? I do the energy operators. Well, these are linear. So because they're linear operators, we should be able to do, yeah, it should just be EM of A, A, M, B, B. EM, there should be, if we do the energy operator on both of these, we should get energy A, energy B, but we know that the energy is equal to what? This is 2n plus 1 over 2 h bar omega. equal to this. So if we knew that, this would be equal to so if we just divide out we should have this is equal to this plus this, right? So this would mean well, that obviously isn't going to work because we need to have the waveforms. So I don't think this approach is going to work because they are evenly spaced in energy. So of course they're going to be lower states. They're going to add up to higher states, but it's just going to be the function that's different. So yeah, I don't know. Maybe we have to do this full formula. Is there anything to do with the lowering operator? Oh, what would it mean to be orthonormal? Commutation. Yeah, I can't think of how to solve this. All right. See how they do it. Okay. So once again, we're doing this. We commute through, we get I think we can make this minus 1 at n minus 1 like that. Oh. If m doesn't equal n at some point, one of these they go to 0. Is that what I'm thinking of? Oh, and I can just cancel these. So this is just going to be equal to so this is going to be so I'll just assume m greater than or equal to n. So whichever one's the biggest, and then we can just do so if m doesn't equal n, this will equal 0, therefore it all equals 0. Is that the idea? Now after acting on, we end up with a state that's proportional to the nth excited, and our equation then calls. Okay. We can, okay, so, all right. So the key, I'll just put as the key solving this was commuting through. Okay, I think I'm just gonna put a pen in that, so to speak, for right now, and I will go back later. I'm just going to take a few minutes to talk about my plan for, maybe I'll leave this open here like this, talk about my plan for next week. Now, I mentioned I was thinking about this, and this is a challenging class. I'm finding it very challenging. You can see how much I'm having to look at the solutions to sort of help me out. Some of this is related to rustiness of earlier material, but like this one, for instance, is purely this stuff. Like this was a solution that depended on understanding how the operators worked and things you can do with the operators. So this is not stuff from any other previous class. So I can't really say, oh, I'm rusty in X or Y. So that's why I am going slow through this. So I don't really feel like going through different material is going to be valuable right now. I think the main value is going to be go through these problem sets, maybe even try to tackle those same problem sets again. I think that will help me kind of understand how to work these problems a little better. I'm thinking that I want to maybe do more next week than I'm doing right now. I've been doing these kind of 3-hour sessions. Next week, let me look at my calendar, see what I have to do next week. So it doesn't look like I have any major tasks in the upcoming week, which may mean that going kind of full bore for next week is the right move. So I'll think about this over the weekend a little bit, but I might be starting earlier on the Monday, and I might just do it as much as I can, because basically I just feel like this is going to take more work to really get comfortable with this than I think I have in 2 weeks. I'm going a little bit too slowly through it. There's still a little bit too much stuff to kind of master in these problem sets. So I think I'm going to stick with the same work, I think, right now. I don't think I really want to change the work that I have to do. But I will go back and kind of go through the problem sets to see that I can really feel comfortable with things, really feel like I'm comfortable with the kind of equations, with the math, that kind of stuff. So I think the approach right now, I'm not going to commit to a schedule yet, but approach, I'm just going to put plan of action. So my idea is 1, finish up to P set 10, 2, do Feynman's on all conceptual weak points. 3, I'm going to make a list. Technical points. So I might have to work harder at this. I might have to put in more time. And I think next week would be a good time to do that. I haven't really been going at the full pace I was doing for the MIT challenge. I mean, this class is super hard. I honestly, I can say, I remember doing the MIT challenge. I never had a class that was this challenging for me. And I think that, as I said, some of that is some of the factors that I mentioned, that I'm now fully into the physics stream. I'm missing one of the prereqs. Basically, I'm just sort of taking the things that I found challenging in the MIT challenge, but taking them up a notch, taking them to a higher level. But on the flip side of it, I've got more time. So I don't know whether there were really any classes that I did over a month in the MIT challenge. It was usually the case that I was spending, I mean, later on, I might have been spending 2 to 3 weeks, but I also wasn't studying as effortfully. So I would say that the kind of, at a full-time schedule, my median pace was probably about class every 2 weeks-ish. Some of them were a bit faster, some of them were a bit slower. And so I think I might want to work more on this next week, because next week also gives me some flexibility. If I work on it like good pace over next week, then I still got another 7 days. And then if things get busy in my schedule, I can kind of accommodate it a little bit. But yeah, so definitely challenging. Definitely feeling like there's still a lot of weak points that I want to work on, a lot of conceptual ideas. This problem that I was struggling over here involved playing around with the commutator to get things to annihilate. So this is not new math. This is math that came up in this class. But when I look at my attempted answer, I'm not even trying that. I'm not even attempting to solve it that way. So I think the right way to think about physics class, particularly classes like this, where there's no longer just a straightforward path to solving every problem, you want to avoid certain difficulties, is just to really get familiar with a lot of these patterns. Because if I can build up that library of patterns in my head when I'm solving a problem, I'll have a lot more entry points, a lot more routes, a lot more paths forward. Some other things I need to work on: getting better with dimensional analysis. I think any problem where I'm trying to solve things that have integrals, solve things that are involving constants, I should be doing dimensional analysis. That's just, and I did do that on this question before. Here, where was it? Yeah, here, I did do the dimensional analysis, and that was kind of how I could tell that my answer was going astray. So I need to start with that. I need to work on the dimensional analysis. Maybe going back and doing a few more practice things with some of the basics of Calc 1 and Calc 2. But I think for right now, just getting through the problem sets at the pace that I'm doing right now, if I put in some more time, I can probably get through them in the middle of next week. And then if I can get through those middle of next week, I can start drilling down a little bit more. I think what I would like to do is probably get up to problem set 10, spend a little while doing some drills, and then redo the problems, trying to do it without the solutions, and then see how well I can do them. Doing the same problem sets twice is a little bit, because you kind of know what the trick is. And a lot of these, you got to figure out what the trick is. They're like a little puzzle. So this puzzle, for instance, was knowing that this is what you got to do. You got to do this with this operator method to try to figure out, try to show this orthonormality. That doing what I was doing, which was, trying to put the closed form, this just dead ends. This doesn't lead anywhere. So I think there is some risks of doing that. So I'm not going to necessarily do all of the problems over again, because just doing them a second pass doesn't seem to be, it's going to eliminate some of that. So what I might do is I might try to supplement some of them with problems I haven't done in here. I might try to look at some of the problems that we don't have solution sets for. So I downloaded a number of previous midterms, previous exams. I couldn't find any more problem sets, but previous midterms and exams would be good, because it'll give me a sense of the difficulty too. Because these problem sets, there's no formula sheet. There's no, they can be arbitrarily hard almost, just because the expectation is that you're working on it with other students, you're getting advice and recitations, this kind of thing. So I feel, I feel like I'm challenged right now, and this is hard. But I think if I, double down and really kind of put in a full effort next week, I'm hoping I can make enough progress that we're going to be at sort of exam readiness in the next 2 weeks. Well, how long do I have? I've got 2 full weeks and then 2 days. So if I don't count those 2 days, let's say those 2 days I should probably be ready by then. So those will be kind of my runway times. So we're kind of at the halfway point, if I consider it like that. So if we're at the halfway point, then that means that I've got another 2 weeks to work on this. I mean, yeah, there's a lot of stuff that's really challenging, but there's also a lot I'm learning right now. So I'm hoping in 2 weeks I'll be a lot better and can be closer to exam shape at the end of 2 weeks. So I'm going to take a break for this weekend. Thank you, everyone, the few of you who are watching me go through this process, watching me struggle. And I will be back on Monday. And yeah, I might be doing a bit more hours so I can try to catch up with this.